The first robotic spacecraft to land on Mars and return scientific information about the red planet occurred in 1976 when two identical Viking landers safely touched down. During the next few years, cameras and other instruments on the spacecraft were used to study Mars' geology, chemistry, biology, seismology, and meteorology. Each lander had a pair of radioisotope thermoelectric generators, or RTGs, to produce the electricity needed to operate. Although difficult and expensive to manufacture due largely to their radioactive fuel source and associated safety concerns, RTGs have the benefit of extremely high reliability. They are completely passive with no moving parts. RTGs also produce copious amounts of heat, which was important for keeping Viking lander components warm enough to operate on the very cold surface of Mars. The landers were built by Martin Marietta, now part of Lockheed Martin. A work-in-progress 3D digital model that I am creating of the Viking lander is used to illustrate the lander and its two RTGs. Radioisotope in RTG refers to the radioactive material used as fuel, in this case plutonium. An RTG needs a source of continuous high heat, which radioactive materials produce while undergoing radioactive decay. The primary isotope of plutonium used was 238. Each atomic nucleus contains 94 protons, which define the element as plutonium, plus 144 neutrons, for a total of 238 particles. Plutonium-238 has a half-life of about 88 years, which means that during a span of 88 years, half of the atoms in a sample will spontaneously decay into uranium-234. As the plutonium gradually decays, the heat of decay will lessen. This limits the useful lifetime of the RTG. Thermoelectric describes the physical process by which thermal energy from the fuel decay is directly converted into electricity. An electric current is generated when there is a temperature difference across two blocks of semiconducting material that are joined at one end. This is termed the Seebeck effect. The type of RTG used on the Viking landers was called a SNAP-19 Viking RTG. SNAP, or Systems for Nuclear Auxiliary Power, was a program from 1956 into the 1970s managed by the United States Atomic Energy Commission, later transferred to the Energy Research and Development Administration. A number of RTG designs were developed. The Viking RTGs produced about 40 watts of electric power at 4.4 volts DC at the start of the mission. The SNAP-19 family RTGs were produced by Teledyne Energy Systems, formerly Martin Nuclear Division. A total of 5 flight-ready SNAP-19 Viking RTGs were built. At the core of the RTG is a fuel capsule containing a stack of 18 fuel pucks. Manufacture of the capsules and final processing of the plutonium fuel was done by Mound Laboratory of Monsanto Research Corporation. The fuel stack had sufficient plutonium to produce 682 watts of thermal energy. The fuel form was plutonium molybdenum cermet, or PMC, consisting of plutonium dioxide particles in a molybdenum matrix. Molybdenum was added to stabilize and raise the melting point temperature of the plutonium alloy. This ceramic form was chosen for safety. The RTG was designed with many features to prevent release of fuel, which will be explained. But if a launch accident did cause an RTG to break completely apart and release fuel pucks, the ceramic fuel form would tend to fracture into large pieces that are not easily inhaled, which is the primary plutonium health hazard. The fuel was hot pressed into discs. Shims of molybdenum were inserted between some of the fuel pucks to fill the capsule volume. Seen here are the 5 shims used in Viking fuel capsule VF3. A total of 8 flight-ready fuel capsules were produced. After some testing, capsule VF3 was opened and its fuel reused to produce VF8. The fuel stack was contained within a 4-layer capsule. The inner liner was made of a molybdenum-rhenium alloy in 2 shells that slip-fit over each other to enclose the fuel pucks and shims. The body and cap of the second layer, the liner, were made of a tantalum tungsten alloy and welded together around the inner liner. This liner formed the primary decontamination enclosure for the plutonium fuel. To vent gas produced by the fuel, a pressure relief device, or PRD, was fitted through one end of the liner and into a hollow space in the topmost fuel puck. The dominant method of plutonium-238 radioactive decay is by spontaneous emission of an alpha particle, the nucleus of a helium atom. The remainder of the plutonium atom becomes uranium-234. Over the course of months and years, enough helium gas is produced to potentially damage a hermetically sealed capsule. A PRD was added to allow the helium to disperse into the much larger volume of the sealed RTG housing. The green tint of the PRD in this 3D model represents some uncertainty in the exact configuration and dimensions used in the SNAP 19 Viking RTG. The capsule's third layer was termed the strength member, formed of an alloy of tantalum, tungsten, and hafnium known as T111. As the name suggests, the strength member provided the primary structural integrity of the fuel capsule. The strength member body and cap were welded together and strong enough to withstand a major impact, such as a fall from great height onto a hard surface or an explosive shock during a launch accident. The fourth and outermost layer, termed the capsule clad, was made of a platinum-rhodium alloy. It served as an oxidation barrier for the overall fuel capsule. The strength member and capsule clad layers had small holes drilled in one end to vent the helium expelled by the capsule liner's pressure relief device. In the event of a launch mishap, burning rocket fuel or atmospheric re-entry heating might weaken or melt the RTG fuel capsule, even though its metal alloys could withstand high temperatures. To guard against such risks, the fuel capsule was enclosed within a graphite heat shield. 3 pyrolytic graphite sleeves surrounded the capsule. This material can withstand very high temperatures and is simultaneously a good thermal insulator across its thickness and a good thermal conductor across its length. High external temperatures would not be readily conducted into the fuel capsule, and any localized hotspots would even out lengthwise, reducing peak temperatures. A hollow hexagonal shield made of fine-grained POCO AXF-Q1 graphite surrounded the sleeves. End plugs of the same material completely enclosed the fuel capsule. The heat shield could tolerate very high heat loads via ablation, where the material surface slowly vaporizes and carries away heat. The combined heat shield and fuel capsule was termed the heat source for the RTG. During RTG manufacturing, some amount of moisture and water vapor inevitably gets trapped within the RTG and some of its materials. This reduces the power output of the generator. A so-called getter was located on both ends of the heat shield, consisting of a zirconium ring within a palladium housing. The zirconium reacts with the moisture's hydrogen and oxygen atoms, getting or removing them from the RTG interior gas mixture. 6 essentially identical thermoelectric conversion modules surrounded the hexagonal heat shield and actually generated the RTG's electricity. Each module had a body made of rigid Min K1301 insulation by Johns Manville, which was shaped to hold 15 thermoelectric couples. The RTG thus had 90 couples in total. The inboard end of each couple was pressed against a thin sheet of electrically insulating mica on the adjacent face of the heat shield. Each couple consisted of 2 halves or elements, an N or negative leg and a P or positive leg, made of different semiconductor materials. The elements' inboard ends were joined via a hot shoe. The semiconductor materials slowly degrade during years of sustained exposure to high temperature. The tags 85 material in each P element very slowly sublimes, turning directly from solid to gas. As a result, RTG electrical output gradually diminishes due to the shrinking amount of material in each element and due to the smaller elements decreasing thermal conductivity, which reduces the magnitude of the Seebeck effect. The outboard, or so-called cold ends of each couple element, were electrically connected by copper straps to form a combination parallel series circuit. 14 of a given module's 15 couples were grouped into 7 pairs, highlighted here by color. The 15th couple was paired with the 15th couple from an adjacent module and connected via number 9 gauge copper wire. Within each pair, the N legs and P legs were connected in parallel. The 45 total couple pairs from all 6 modules were connected in series, forming a circuit that produced 4.4 volts DC at nominal temperatures. The circuit included a magnetic compensation loop to minimize the external magnetic field produced by the RTG, which could interfere with other Viking lander systems. The generated electricity was routed out to the lander via 20 pins of a 26-pin Deutsch hermetically sealed electrical receptacle. The remaining 6 pins were used to provide telemetry from 3 internal instrumentation devices described later. Generating maximum electricity required the largest possible temperature difference from the hot inboard end of each couple's semiconductor elements to its relatively cold outboard end. To achieve this, an arrangement of cold end hardware was used to conduct heat from the couples to the RTG's external housing, which then radiated heat into the environment, thus passively cooling each thermoelectric element's cold end. Each of the N and P leg elements had an identical 3-part cold end assembly. An aluminum alignment button was pressed by an aluminum piston against the adjacent copper strap surface. The button and piston mating surfaces had spherical contours to accommodate slight misalignment. A stainless steel spring pressed the piston and button against the copper strap for good thermal conductivity. The springs also kept the thermoelectric couple elements in hard contact with the heat source as the semiconductor material degraded over time. Each module had an aluminum heatsink bar which held the 30 button piston spring assemblies. The outboard surface of the heatsink bar was cylindrically curved to match the inside of the RTG's housing, to which the bar was in direct contact. The aluminum cold end components were subjected to a hard coating process that formed an electrically insulating oxide layer. The threaded holes in each button and the small holes in the pistons and heatsink bar were to facilitate RTG core assembly. Temporary bolts were passed through the bar and piston and threaded into each button. Nuts on each bolt were adjusted to compress the springs and hold the pistons and buttons in position. A core assembly tool was used to arrange the 6 heatsink bars and associated thermoelectric conversion modules in position surrounding the empty heat shield. This photograph shows Victor Renzi of Teledyne Energy Systems making adjustments to an RTG core during assembly. The bolts could then be removed and the core inserted into the housing. Spring pressure held the core in place. Additional RTG components could then be installed. The RTG's exterior housing was made of a magnesium-thorium alloy called HM21A, chosen for its low density, high strength, and high thermal conductivity. Thorium is weakly radioactive, and thus the 2% thorium content in HM21A requires special care to be taken during fabrication. However, the finished metal does not present significant radiological risks. The RTG's 6 large fins radiated heat to keep the outside as cool as possible, improving the thermoelectric yield. Even so, the RTG's exterior temperature was typically around 300 degrees Fahrenheit or 150 degrees Celsius. This external temperature is the principal hazard of handling a fueled and sealed RTG, more so than radiation from the plutonium fuel or thorium in the housing. Practically speaking, no amount of careless handling will rupture the fuel capsule. The exterior heat may seem mundane in comparison to the famous characteristics of plutonium, but the RTG is simply very hot to the touch and remains so for decades. Another factor that can limit the useful lifetime of an RTG, besides fuel decay and thermoelectric degradation, is the helium gas produced by plutonium mentioned earlier. Helium has a relatively high thermal conductivity. A buildup of helium within the sealed RTG would tend to even out the internal RTG temperature, decreasing the thermal gradient across the thermoelectric couples and reducing the electricity generation. There is not much empty volume within the RTG housing, but there is enough for the choice of fill gas to matter. Argon is much less thermally conductive, readily available, and essentially non-reactive with all other materials, and so the RTG would ideally be filled with argon when the RTG was sealed. However, a reduced core temperature was actually desirable during months of Earthbound warm environment testing and storage prior to spacecraft launch. Therefore, the RTG was filled with a 90% helium, 10% argon cover gas mix. To counter the deliberately high helium fill and the slow production of additional helium as the fuel decayed, a sealed reservoir dome was welded on top of the RTG and filled with a 5% helium, 95% argon mix. A so-called controlled leak device was installed in the RTG upper cover, which permitted a very slow interchange of gas between the reservoir and housing through an O-ring. Argon from the reservoir would permeate into the RTG, and helium within the RTG would permeate into the reservoir, increasing generator efficiency as the mission progressed. The 5% helium content within the reservoir facilitated checking for dome weld leaks during manufacture. Despite the fact that the RTG was completely passive and that no intervention or remediation could be done in the event that problems developed after launch, some instrumentation was included to enable ongoing assessment of the RTG's condition. A pressure transducer was installed within the housing lower cover to monitor the gas pressure within the RTG. I have not been able to identify the exact model of Bourne's Instruments transducer used, so a generic model of the approximate configuration is shown in green. Here are plots of gas pressure of Viking Lander 1's pair of RTGs during the first 4.5 years on Mars, from July 1976 through January 1981. As can be seen, there is considerable variation between the two units, with RTG serial number 111 starting at about 6 pounds per square inch absolute or PSIA versus 16 PSIA for RTG 112. Both show a gradual increase in pressure of about 2 PSIA for RTG 111 and 8 PSIA for RTG 112. To monitor the temperature at the hot inboard side of the thermoelectric couples, a hot junction resistance temperature detector, or RTD, was welded to a tab on one of the couples. The RTD is a platinum wire-wound unit, model 132FG, made by Rosemount Engineering Company. Here are plots of the hot junction temperature for Viking 1's RTGs, daily maximum and minimum values, during 4.5 years. RTG 111 was somewhat hotter at about 1000 degrees Fahrenheit or 540 C versus about 970 degrees or 520 C for RTG 112. The third internal instrumentation device was a glass bead metal oxide thermistor, VECO model TX1737, located in a slot in the inside surface of the RTG housing adjacent to radiator fin 5, I believe. This measured the so-called fin root temperature, essentially the relatively cold outboard side of the thermoelectric couples. Here are plots of the fin root temperature for Viking 1's RTGs, daily maximum and minimum, during 4.5 years. Both RTGs average about 300 degrees Fahrenheit or 150 C. Signals from the 3 internal devices were routed to the lander via 6 pins on the RTG's power output electrical receptacle. The final RTG instrumentation device was the hazard monitor thermistor, of the same type as the internal fin root thermistor, located in an exterior slot near the root of radiator fin 3. It was used to monitor the fin root temperature during testing when signals from the RTG's internal devices were not available. The 2 RTGs on each of the 2 Viking landers operated very well during their multi-year mission. Here are plots of the combined electrical wattage generated by the pair of RTGs on each lander, showing daily maximum and minimum. For Viking 1, from an initial 80 watts on landing day in July 1976, the output gradually decreased to 63 watts by January 1981, when regular RTG monitoring was stopped for budgetary reasons. The RTGs enabled Viking 1 to continue operating until November 1982, when a programming mistake during a refresh of the lander's computer software occurred and radio communication was permanently lost. The output from Viking 2's pair of RTGs dropped from an initial 82 watts at the time of landing in September 1976 to 68 watts by February 1980. At that time, the lander's rechargeable batteries, necessary for spacecraft operation, failed to hold sufficient recharge from the RTGs, and radio contact with the lander was lost. I am grateful to a number of organizations for allowing me to conduct research on the Viking artifacts they have preserved.